noodles on a gas stove. The gas that the stove gives off or uses is methane gas, also known as CH4. This contains 1 atom of carbon and 4 atoms of hydrogen. And when the gas is released, it goes through combustion. The combustion equation of the gas is CH4 plus 2O2 yields CO2 plus 2H2O. This occurs when the methane is released and into the oxygen. Okay, so I'm going to put my noodles in. I'm waiting for the water to boil. So once the pot of water is on the stove, it uses pretty much all 3 types of heat transfer. The pot is touching the stove part, the hot part of the stove, and so that is conduction. And because the heat is being transferred through a conductor, and the water molecules are heated, and when they get hotter, they collide faster, making the water hotter. And it's also radiation because once this is boiling, you can, and actually right now you could feel the heat while you put your hand over the pot. And so right now I'm boiling 3 cups of water for about 2 minutes to see if that is as long as it takes. And it might take a little longer. Now I'm going to put my noodles in.
So welcome to Cooking with Chem. I'm Jace Richards, and today I'm going to explain how we found the pH level of Mountain Dew and how it has unhealthy effects on your enamel. And we're also going to show you how boiling water in the microwave is faster and more efficient than boiling it in a pan on the stove. So the purpose of this video is to show that Mountain Dew can be good tasting but also damaging to your teeth. And it's also to prove that boiling water in the microwave can be faster than boiling it on a pan. So first, I'm going to explain how we found the pH level of Mountain Dew. What we did was we put Mountain Dew into a beaker, just I think 5 milliliters, and then 5 milliliters, and then we diluted it with another substance, and then we put NaOH, or sodium hydroxide, into a dropper, and we slowly dropped the sodium hydroxide into the diluted Mountain Dew until it was neutralized, and you could tell it was neutralized when it started to turn a pinkish, purplish color, and when you shook it around, it didn't dilute with the other substance. It just was neutralized and stayed pink and purple. And so after we did that, we saw how much milliliters of sodium hydroxide it took to neutralize it, and then we took the average of 3 tests and we put it into the equation that we used to find the acidity, and the pH level ended up being about 3.1, which is super damaging on your teeth. What would happen was the enamel, to stay healthy, has to have food come in at about a 5.5 acidity or pH level, and a 3.1 would really be damaging on it. So it just proves that as good as Mountain Dew tastes, it's really damaging on your teeth. It's pretty much like drinking close to battery acid, and so it wouldn't be good for your teeth. And so that's pretty much how we found the pH level of Mountain Dew. Alright, now I'm going to show you how boiling water in a microwave is faster than boiling water on the stove. So first, we'll get a microwave safe bowl. And then we'll get a pan, or I guess a bigger one. So we'll get a measuring cup. And we'll fill it up with with 5 cups of water. There's 5. Okay, so we'll start the heat over here on a burner on high, and then we'll put this in the microwave for 3 minutes. Alright, so we still have 1 more minute on the microwave, and this has been on there for the whole time, and it's just starting to kind of steam up, but it's not boiling yet. So basically what this proves is that if you're cooking, I guess, the boiling water on the stove isn't as efficient and quick as it is in the microwave. And basically the reason for that is the molecules when you put it in the microwave, the temperature rises faster in the area and the molecules bounce together faster because of the kinetic energy rising. And so when the molecules bounce together faster, it makes the heat in the water boil faster. And that doesn't happen with this because the area around this boiling water is room temperature, and just underneath the water is actual high temperatures. So that's why it doesn't boil as fast. So we can take this out. It just came down from a boil. It has little bubbles all in it. And this one, if you want to come look, is still not bubbling. So it just proves that cooking in the microwave is a lot faster than cooking on the stove.
Alright, so I am cooking the meat for the spaghetti, just regular ground beef, like you would stick in the sauce. Oh goodness, I can't rotate this right. Anyway, let's talk about what is actually happening here. We cook meat because of the nature of proteins. Now, proteins are made up of amino acids. And these amino acids bond together to form a long chain, like I'm going to use a cord here as an example. Now, there are 3 levels of structure in these proteins. The first is primary, which is just a long cord. It's easy to digest. That's what we eat. The second is secondary, which is more like secondary structure. If we take it and we twirl it like this, if you can see that, kind of all twirly and such. And the third and final structure of proteins is called tertiary, and it looks more like, say, this. That is what occurs when these they're little functional groups that bond together along the amino acids, and they give it the protein its unique function. What happens, as you can see here, what's happening right there is we are taking all these bonds between the functional groups and we're heating them up until they break apart and form just a secondary structure, and finally a primary structure. And the primary structure is what we eat. We just about even. Alright, that's cool. Now I'm cooking the sauce for the spaghetti. As I cook, I will find the specific heat of the sauce, which I suppose to be around 1, considering the high water content. I know the mass is 680 grams according to the can. See it right there. I guess you can't. Anyway, it's 680 grams. I'll measure the beginning and ending temperature to find the change in temperature. The equation used to find specific heat or heat transferred is Q equals mc delta T. I'll show you that here. Oh! Alright, so Q is the heat transferred, m is the mass of the substance, c is the specific heat, delta T is the change in temperature. Alright, so that equation can be manipulated into C equals Q divided by the mass change in temperature. I'll heat the sauce for 2 minutes before checking the ending temperature, which I'll find with just a simple food thermometer. Okay, so here we are 2 minutes after heating the sauce. It started at a room temperature of about 72 degrees. Oh, that's not it. That's it. And ended at about 110 degrees. Now this is in Fahrenheit, of course my thermometer is in Fahrenheit. I heated it for 2 minutes and it had begun to boil and kind of spill everywhere. So now I have a mess to clean up. But anyway, I'll do some calculations and find out exactly what happened. Alright, after some calculations, I found the specific heat of the sauce to be about 1.1 calories per gram degree Celsius, which is actually close to the specific heat of water as I had supposed, which is about 1 calorie per gram degree Celsius. You can see my calculations here. There's a difference of 38 degrees between the initial point and the ending point. Also, when we cooked the noodles, we discussed combustion and heat transfer. We also discussed the concept of pH and titration and applied these to a common soft drink. As we prepared the ground beef, we discussed the structure of proteins in the denaturing process. And finally, as we cooked the sauce, we found the specific heat and discussed the equation Q equals mc delta T. Now this has been our group cooking with chemistry, I suppose, and that's us making spaghetti.